Today we're going to talk about.
Can you
Yeah, I'll start again. All right, thank you for having me. Today we're going to talk about the nerves of steel conjecture and some work towards it. So let's start off with talking about what the nerves.
Can you put a finger on the video box on your screen that is showing me, and
yeah, sorry.
And
one second.
Take it to the other side.
My bad.
Just perfect.
Over here or off?
Perfect. This is perfect. Yeah.
Okay. So towards the nerves of steel conjecture. Let's start with some introduction and background. So we're going to say that.
Oh, sorry, we lost your video now.
Wait. Why?
When you're removing the box, are we losing your video as well?
I can try and minimize it. Is this working?
Even if you move that box to the side, I don't know why your video is going away as well. Okay, let's keep that in a minimized form. Yeah, let's keep that in a minimized form. Yeah.
Sure. All right, we say that a tensor triangulated category, or TT category, is a triangulated category C together with a symmetric monoidal structure tensor from C times C to C, which is exact separately in each variable. And such that C is rigid. That is, every object has a dual. And then what it means to have a dual is you have the usual axioms. You have like a co-evaluation like this, and an evaluation map. Such that X is going to split off like this. Oops, the way I wrote it, I should do it the other way. Now, if we have such an object like this, Balmer associates to such a C, the Balmer spectrum. So this is a space denoted by SVC of C for spectrum of C. And as a set, its points are the set of thick prime tensor ideals in C. So what it means to be a tensor ideal, it means that if we have any X in our ideal P and any Y in C, then X tensor Y is in P still. For it to be prime, it means that if X tensor Y is in P, then one of them is in P. And for it to be an ideal, all right, well, thick means that it's closed under T summons, and being an ideal means that it's closed under the 2 of 3 property. So if I have an exact triangle like this, then X and Y are in P implies that Z is as well. And of course, it's closed under suspension, so the suspension of X is going to be as well. Okay. Now, motivated by nilpotence phenomena, and the hunt for residue fields, Balmer defines another space. Associated to a TT category C. And this is called the homological spectrum. Now, to define the homological spectrum, we start by taking this united category here of additive functors from C off to abelian groups. C embeds in here by the unit embedding, which I'm going to denote by yo. This just takes an object x and C and maps it to unit of x, which is the functor just hom dash x. And using this, we can define a small subcategory here, little mod C. These are the finally presented right C modules, is what this is called. So this is going to be all F in mod C, so all big right modules, such that F is a co-kernel of something, of some map in this image. So I have some unit of X mapping to unit of Y for X and Y in C. Get this here. So of course we still have some unit of map from C into mod C, because I can always take the zero map and just the co-kernel of zero including into unit of X is just unit of X, because unit of zero is zero. Now, there's a symmetric monodal structure called the deconvolution structure. With respect to which this unit inclusion from C into mod C is symmetric monodal. And that's sort of the defining property of the deconvolution structure in a sense. And using this, we can now define the actual homological spectrum. It's going to be, as a set, the set of maximal tensor stair subcategories in mod C. So this is going to be the analog of the Balmer spectrum that we defined before of thick prime tensor ideals, except this time we're requiring a little bit more, requiring it to be maximal. And pulling, so to each point, X in this homological spectrum, we can associate a functor to an abelian category from our tensor triangulated category C, which we can call HX in line with Balmer's notation, which starts by doing the unit map into mod C, and then we quotient out this maximal stair tensor category. So this is just the quotient. And if we pull back the zero map along this, so if we look at everything which maps to zero under this HX, this turns out to be a prime tensor ideal in a prime thick tensor ideal in C, and therefore we get a map psi C here, which is going to compare the homological spectrum to the ordinary Balmer spectrum. And Balmer proves that this map is always surjective. I'm not saying anything about the topology on the homological spectrum, but it is continuous for the topology. And in the same paper, Balmer proposed the nerves of steel conjecture, where he said it would take nerves of steel conjecture not to conjecture that this is always an isomorphism, which then became known as Balmer's nerves of steel conjecture, that this comparison map is always an isomorphism. And this is known this is true in all known cases. So everywhere we've computed the homological spectrum and the Balmer spectrum, we know this to be true. Okay. So we have a bit of a slogan for what this thing is. This is sort of the universal space for detecting nilpotence in C. This is a bit of an imprecise slogan. As opposed to an actual result. But here's the sort of basis for it. We have that if we have a map in C such that it's 0 for all residue fields X, then F is tensor nilpotent. And there's a bit of a converse to this, which says that if we have some collection of residue fields which jointly detects nilpotence in C, in a bit of a strong form, it has to actually be starting from X and C, and then Y has to be something in like a big category. And we have a map like this. And if it detects nilpotence like that, then it has to, if you have some collection of residue fields which detect nilpotence like this, then it has to be the entirety of the homological spectrum. That's sort of this result here. So we're going to talk about this in a bit of a different guise today. And the way we're going to do that, we're going to need one more condition. So we're going to say that TT category C is local if for all X and Y in C, if X tensor Y is 0, then X is 0 or Y is 0. This is equivalent to saying that 0 is a prime ideal. Which is also equivalent to saying that the spectrum of C has a unique closed point. So this condition here is sort of like Nakayama's lemma. Now, given a local tensor triangulated category C, we're going to say that the exact nilpotence condition holds for C if whenever I'm given an exact triangle starting from some object Y here, mapping to the tensor units, mapping to X, then there is a non-zero object Z in C, such that either Z tensor F is tensor nilpotent, or Z tensor G is tensor nilpotent. And Balmer proves that the following are equivalent, that the nerves of steel conjecture holds. So you can also talk about the nerves of steel conjecture holding for a particular category, which is that the comparison map is an isomorphism for that category. This is the statement that it holds in general. And that condition is equivalent to the exact nilpotence condition holding for any local TT category C. So the idea here is that if we have an exact triangle like this, then one of the maps is tensor nilpotent in a residue field over 0. So over this unique closed point. And if we can find the unique one, well, we can basically find a unique one if and only if we can find some z with the condition before. And then to reduce the local case, you use a fact about pulling back, how pulling back along a map like this, C to C mod P, how this also restricts to a pullback on the homological spectra. So you have some diagram that looks like here, let me draw it over here maybe. Use some diagram like this. Okay. So let's talk a little bit about improving this result. So here I just have Balmer's result written again. And we can add in a third condition here. This is going to be a strong form of number 2. The exact-nilpotence condition holds with the global bound. So there exists some n such that for all tensor triangulated categories C, and all fiber sequences, or all exact triangles, let's say, there is a non-zero object, local, you say local TT categories, Z and C, such that either Z tensor G tensor N semi q0, or that the nth tensor power of F is tensor Z is 0. So as opposed to just one of these two being tensor nilpotent, we're actually requiring that some specific tensor power of them is 0 for some fixed n, which does not depend on C, does not depend on the fiber sequence. And let me remark, we currently do not know any examples where n is greater than 2 fails. Or let's say n equals 2 fails. You need n equals 2 because there's some examples such as the stable module category of the cyclic group CP over a field of order P. But aside from that, and okay, there's some similar examples, but we don't know any examples where we need n is greater than 2. N equals 2 seems to work for what we know so far. So it's possible n equals 2 works. At one point it was suggested maybe n equals 3, but who knows? So let's talk about some background on this result. All right, so these two are Balmer. And this last one is, this last equivalent condition is due to my paper. Let's talk about some background before we start. Ultra products and ultra filters. So let X be a set. Actually, let's do I for index instead. Let I be a set. We say an ultra filter on I. Let me say ultra filter in parentheses. So I'll first define a filter. Is a set of subsets of I. such that, first of all, we want I to be in U and the empty set to not be in U. Secondly, it has to be closed under taking supersets. So if A is in U and A is a subset of B, then B is also in U. We want it to be closed under the finite intersection property. So if A and B are in U, then so is their intersection. So this right here is just a filter. And if we want it to be an ultra filter, we want it to be somehow maximal. So this is condition 4, that for all A is a subset of I, either A is in U or I minus A is in U. So some examples that we have of just trivial ultra filters. Let's start with like the natural numbers of I, because this is what's going to be the case we're most interested in today, especially. Then we have the principal ultra filters. This works for any set. This is the set of all subsets such that n is an A. And you can quickly verify that, well, the empty set does not contain n. The whole set contains n. Any set which contains a set which contains n also contains it. Finite intersections and this this ultra property. You can easily check that these are satisfied. And sort of these are the only ones you can write down by hand. Because if you want any others to exist, it's a form of the axiom of choice. It's actually a slightly weaker form than AC, but it doesn't really matter. So if you want to construct others in general, what you do is you start with F. This is going to be the set of cofinite subsets of n. This is a filter. And then using axiom of choice arguments, you can extend this to some non-principal ultra filter. And this is what we're going to have to do today. Okay, so how are we going to use this? Let's talk about ultra products now. So definition, let U be an ultra filter on an index set I. Then, and let's take Ci for I and I, a collection of tensor triangulated categories indexed by I. It might also be helpful to think about what I'm going to say, how you would define ultra products for Abelian groups or rings or something, if you haven't seen these before. It's a very similar concept. Then the ultra product denoted by the product over U of Ci is a quotient of this category here. So we just take the product over I and I of these Ci's by a certain thick tensor subcategory. Which I'm going to denote by, let me denote by like JU. It's not a T. I know sometimes the math T looks like a J, but this is supposed to be a J. Okay, so I'm going to define JU as just the set of objects in this product such that the set of all a and I, let me say I and I, such that xi is equivalent to 0. I want this set to be in the ultrafilter U. So I'm saying that it's 0 if it's 0 on something in the ultrafilter. And one can check that this is a thick tensor ideal. Okay. And now the main point we're going to want to use this today is if all Ci are local, then this is a prime ideal. Indeed, suppose we had some objects here, xi and yi, which tensor to something which is in this Ju, which means that the set of set of I such that the tensor product here on the product is pointwise. So xi tensor yi sim equals 0. This is in our ultrafilter. Well, let's assume that xi is not in Ju. Then the set of I with xi0 is not in U, and therefore the set of I with xi not 0 is in U, because this is just the complement, and our filter was an ultrafilter. Therefore, the set of I such that xi not equivalent to 0, intersection the set of I where yi is equivalent to 0, which is equal to the set of I where xi is not equivalent to 0, intersected this set where the tensor product is equivalent to 0, is in the ultrafilter, because this is in the ultrafilter by assumption, and this is in the ultrafilter because X was not. But this implies that, in particular, a superset of this, which is the set of I where yi is equal to 0, is in our ultrafilter. So therefore, Ju is prime. And in particular, since we're modding out by a prime tensor ideal, if all Ci are local, then the ultraproduct of the Ci is also local. So when we're doing this, typically we're going to want to take a non-principal ultrafilter. Everything still works if you do it with a principal one. It's just that the ultraproduct along a principal ultrafilter is just the category Ci, where I is the generator of this principal ultrafilter, which is not very interesting. Okay. And now let's take this statement here again. Yay. Okay. So the first two parts are due to Balmer. And we're going to prove that the second and third condition are equivalent now. Obviously, the third condition implies the second equivalent, the second one. because the third condition is just that the exact nilpotence condition holds with the global bounds. Of course, if it holds with the global bound, it also holds overall. For 2 implies 3. Suppose towards a contradiction. That for all n, there exists a tensor triangulated category C, a local tensor triangulated category, Cn, with an exact triangle, Yn mapping by Gn to 1n, and then to Fn to Xn, such that there is no Z in Cn with Z tensor Gn tensor n equivalent to 0, or Z tensor F tensor n equivalent to 0. So because we assumed it was holding, this has to hold with some higher power, but we're saying that it doesn't hold up to order n. Then we can take some non-principal ultrafilter, U on the natural numbers, and let C be the category which is the ultra product over U of all of these CNs. Then, by what we said before, C is local. And we have a fiber sequence. We have some exact triangle. It just looks like this. It's just the product of all the exact triangles we defined before. And if we're assuming that 2 holds, then there exists some object, Zn in here. So when I'm writing Zn, this is just a lift of whatever object we're getting in the ultra product. There's many objects which would work for this because I can always modify it by something which is, I can always modify it by something non-zero outside of a set, on a set which is not in the ultra filter. In particular, I can also assume that every Zn is always non-zero, because if it's non-zero, then it's going to be non-zero on something in the ultra filter. So this is just the exact nilpotence condition holding in C. And I'm assuming without loss of generality up to taking duals that this first case happens. So Zn tensor Gn tensor K is equivalent to 0. So this condition here says that the set of n such that Zn tensor Gn tensor K is equivalent to 0 is in the ultrafilter U. Since we said that Zn was not equal to 0 in C, this also means that the set of n such that Zn is not 0 is in U. So the set of n, such that both of these conditions hold, is in our ultrafilter. But our ultrafilter in particular was non-principal. It contains every set in U is infinite because it was an extension of the cofinite filter. So there exists some n in this set. We'll call it M, I guess, so that I can distinguish it a little bit. With M greater than K. But then I'm saying that I have some Zm, which is not equal to 0 in Cm, with Zm tensor Gm, the tensor K equivalent to 0. And we had previously assumed by construction that there was nothing with this, the mth tensor power, which was 0. But M is greater than K. So this cannot happen. So if the Nernst-Steele conjecture is true, then we get this exact nilpotence condition with a global bound. If we find a bunch of examples where we can push this boundary larger and larger, then we find a counterexample to the Nernst-Steele conjecture. Okay. So I'm going to mention a little bit some of the other things that are proved in the paper for more cases where the exact nilpotence condition holds, and then we'll get into a little bit about free constructions. So it's known, basically, if you have any case where we know where the Nernst-Steele conjecture holds, such as Akil-Matthew proves it holds for modules over a even Noetherian ring with Noetherian pi star, rational E-infinity ring. Balmer proves it in some number of cases. It's known for SH, for equivariant, like genuine equivariant G spectra, in a lot of cases where we look at representation theory. If we know the Nernst-Steele conjecture holds for any of those, then the ENC is going to hold for all of the localizations of those categories. Some more cases where it holds, in my paper, we can extend Akil-Matthews results to show that if R is a rational connective E-infinity ring, so morally, this is just a tensor triangulated category generated by its unit, where the graded endomorphisms of the unit are concentrated in non-negative degrees. And pi 0 of R is a local ring. So in this case, pi 0 of R being a local ring is equivalent to the category being local. Then the exact nilpotence condition holds for R, or rather R mod, which is like perfect R modules. This relies on a couple of facts. So one thing you can show is that if you have some maps like these, some filtered colimit of local categories along local maps, which are just faithful maps in this case, just says that if f of x is, if x is non-zero, then f of x is non-zero. If you have some so each of these are faithful tensor functors, then you can take their direct limits and you're going to get something which is local. And if you have the exact nilpotence condition held for all of these, then it also holds for the direct limit. And then you have to work with finally presented rational infinity rings. And these you can sort of build up cellularly, and then it's a bit of an inductive argument. But one of the cases gets a little bit in the weeds. It ends up requiring Hironaka's embedded resolution singularities. So we're not going to go too much into the proof of this today. Another case for this holds, where we can illuminate a little bit about the argument. Suppose R is a connective, the infinity ring, with pi star of R Noetherian as a graded ring. And perf R local. Then the exact nilpotence condition holds for perf R. So the sketch, because R is a connective infinity ring, if we look in the big category of R modules, then we have this residue field K. We can take R to its truncation. This is equal to pi 0 R. This is something discrete now. This is an ordinary ring. And this is a map of commutative rings. Some more in Lurie chapter 7. And because this is an ordinary ring, we can quotient this out further to a residue field for this. It's an ordinary ring, it's going to be local. We can quotient it out to a residue field. Just by quotienting out finitely many things. Now, if I have any fiber sequence, then upon tensoring with K, either we have that G is going to tensor to 0, or F will. This does not give our exact nilpotence condition yet because K does not have to be perfect. It's just something in the big category. To get back to something perfect, what we do is we're going to take R, we're going to start with pi 0 of R, we're going to take our maximal ideal M. And we're going to choose finitely many graded generators, x1 through xn, living in M. And then we just take this causal object, R mod x1 through xn. This, of course, does not have to be equal to K because this is some sort of causal resolution. If these aren't a regular sequence, then we're going to have issues with torsion coming up with new things. This is not necessarily K. However, we still have that this thing here is a module over pi star of R, or rather pi star of this is a module over pi star of R mod x1 squared, x2 squared, xn squared. Sort of for the fact that if you look at like R mod y, then y doesn't have to be 0 on the cone, but y squared is 0 on the cone. And in particular, we can filter this just by a Postnikov filtration, which is now going to be finite because it's going to be something finitely generated over this ring, which only has finitely many homotopy groups because we've modded out this entire maximal ideal, which hits everything in positive degrees. And we're taking squares. So we might still have some stuff in positive degrees, but it only goes up so far. So we're going to filter this by Postnikov filtration. This is going to give us a finite filtration on this thing, on this causal object, with each associated graded. So these are successive cofiber things. Being a module over pi 0r. And as a module over pi 0r, it also factors over this like mod x1 squared through xn squared. And since it's a module over here, since it's something discrete, each of these has a finite filtration with successive quotients direct sums of shifts of k. And now we can build back up to get that this object is what we can use to test for nilpotence. In particular, if we have some like part in our filtration so far. So this is like the ith step, including into the I plus first step. And here I have some direct sum copies of k. And because we know that G is tensor nilpotent here, so say just G tensor n is equivalent to 0 here. And we also know that G tensor n is equivalent to 0 here. In particular, G is equivalent to 0 after I tensor it with this. I know that G tensor 2n is equivalent to 0 here by a standard sort of triangulated argument. And if we build back up, this tells us that G is tensor nilpotent on this causal object here, but it does not give us a bound on the nilpotence order. Well, I mean, it does, but it gives us a very bad bound. It depends a lot on the actual filtration of this and what each of the individual pieces look like. And it's sort of like this exponential thing in that. So it's not a very good bound, but it tells us that it works at least. Now, with the last sort of 10 minutes, 14-ish that I have, let me talk a little bit about free constructions. And something that the sort of universal case for the nerves of steel conjecture. So here we're actually going to require infinity categories. So far, everything was sort of triangulated. This year I used a little bit of higher stuff, but if you want to do free constructions, you really do need something which is functorial, and for that, we're going to need to use infinity categories. So suppose we want to start with, suppose we want to know the universal pointed object. So we want something which is a sort of universal TT category with an exact triangle that looks like this. Well, to specify this, all you have to do is specify this map F. And to have a map from the unit, this is what one calls a pointed object. So we are looking for a universal category on a pointed object. If we had such a thing, C, which I'll describe how to construct in a second. And in particular, this C is not going to be local, so we're going to have to do what I'm going to do here. Then for any local TT category, D, let's say, if I have this fiber sequence here in D and I want to test the exact-nilpotence condition, this fiber sequence in D is going to induce a functor from C to D, so some exact tensor functor, which takes a universal pointed object to, I really should use a different notation, but whatever, this thing. Because D is local, the kernel of F is a prime ideal. And so this factors over C mod kernel of F. If I knew the Nernst-Steele conjecture held for C, then the exact-nilpotence condition holds for all of the local categories. So for all of these C mod kernel of F. And since it holds for C mod kernel of F, I can find some non-zero object Z in here with the usual properties. And that Z is going to map under F to F of Z and D with the same properties. So all one has to do is really check for this category here. Unfortunately, this category is suitably complicated. So to be precise, this category C is going to be something like pre-sheaves on some category of oriented Bordisms plus to SH. Just to state it a bit imprecisely with the day convolution structure. Now, the reason I add this plus here is because it's not exactly oriented Bordisms. If you look at the category of oriented cobordisms, this is the category of oriented zero-dimensional manifolds. So I just have some number of points with some pluses, some minuses. And maps between them are going to be compact one-dimensional manifolds such that we have boundary of, let me call this M, I guess, or N is fine. So the boundary of N has a decomposition into del1 and coproduct del2n with minus del1n is equal to M0 and del2n equals M1. So we could have something like this here. This is the free thing on a rigid object. Sorry, on a dualizable object. The reason why we have to have this is because this here is like so the empty set here is the dual. Sorry, this is the unit. This is the free object here is the plus, minus here is the dual. The way you do the tensor product here is just by taking coproducts. So this is the tensor product of this dual, and this is the evaluation map. It's this interval here bent over itself, going back to the unit. And then if you look at the empty set over here, so this is again just the unit. Here's the co-evaluation, such that a circle here is just giving this sort of free trace. And what we do for this plus, we also need to include the free thing on a pointed object. So we also need a free map from the empty sets to a positively oriented point. To do this, you also allow intervals. So this allows half open intervals. with positive orientation on the endpoint. So something like this is our free map from the empty set to the positive point. Now these are not the worst to write down, but their Balmer spectra are a little bit extremely complicated. This is going to be studied by work of Ko Aoki, Anish Shetalavada, Tobias Bartel, Greg Stevenson, and Tomer Schlank in upcoming work that they're calling higher Zariski geometry. And in particular, they're going to study not quite this one, but at least the free affine case where we don't have this extra plus. This is the tensor triangular affine line from the universal properties thing. And one thing you can say about this is even in just the rational case, or even just the complex case, is that the spectrum of this surjects onto an infinite dimensional affine space. This is Aoki, Bartel, Shetalavada, Schlank, Stevenson. And the reason for this is just because it surjects onto the graded spectrum of the unit, and the unit is the C homology of the classifying space of closed 1D manifolds. And this thing here breaks up as some coproduct I grade equals 0 of some classifying space of a symmetric group, which this part goes away, so we can ignore this in the homology, times classifying space of n circles, so CP infinity times n. So we're getting, each of these CP infinities is going to give you an extra polynomial factor. In pi2. If you only, it's important to look at the graded version here. If you only look at the endomorphisms of the unit, you're only going to see what's coming out from pi0, which is just going to be a polynomial ring. So you really do need to look at the pi2 part here, because you're getting like, each of these is introducing n polynomial variables in degree 2. All right, I think that's all I have for today.
Thank you, Logan. Let's all unmute ourselves and give the speaker a round of applause. Okay, if you have any questions for Logan, please ask them. Questions or comments, I should say.
Hello. I have a question, but probably is a stupid question. So, I suppose you know there is a work by Bartel and Sanders where they compare the homological and Balmer 5 support. And they showed that the comparison map between the homological spectrum and the Balmer spectrum is just the Kolmogorov quotient of the homological spectrum. So the nerve-hostile conjecture is equivalent to the homological spectrum being T0. And you did not mention anything at all about the topology of the homological spectrum. So I wanted to ask you if this works of yours is totally unrelated to that factor, or if at the end you still got some result about related to this and the topology of the homological spectrum now.
What I have here is not necessarily, it's more so on the set theoretic level, because if you have that it's an isomorphism set theoretically, you get that it's also an equivalence on the level of the topologies. The topology is not much different.
Thank you.
Thank you, Nicola. Any other questions or comments?
I have a question. So, the first result is, so you're saying that the inertia steel is equal to for every prime category having a universal n. Have you thought about, you mentioned that 2 might be the one, but maybe not 2, but have you thought, does some of your work suggest that there is a universal n period which works for every prime category, which may or may not be 2?
Yeah, I don't know what the universal period should be. I mean, 2 seems like it could be reasonable. I think at one point Paul was suggesting maybe it could be 3, but I mean, I would be interested to see if there, just even if there are any examples where 2 fails and we require 3 or especially higher. I think if there's a failure at 3, I would expect the inertial steel conjecture to be false.
Thanks.
Thank you, Jim. Any more?
Maybe just a comment. It would be interesting to know what is the you called it the period. What is this exponent when you do the chromatic localizations of p-local spectra, right? We know it is bounded, but I don't think we know it's 2 there, right?
Yeah, I'm not sure what the